Let's welcome to Mission Control via telephone right now Dr. Ray Sedgwick with the Spheres Rings experiment. Welcome to Mission Control, Dr. Sedgwick.
All right, thanks very much.
We're happy to have you here over the phone. Of course, the International Space Station getting ready to celebrate the 15th anniversary of its first Element launch, and a host of research that's been going on aboard the International Space Station since the first crew members arrived. Mike Hopkins worked with one of the experiments that you're most familiar with a little bit earlier this week. Could you describe your experiment for us a little bit?
Yeah, certainly. So our experiment is called RINGS. It's an acronym. It stands for Resonant Inductive Near Field Generation System. It's a piece of hardware that is being used to demonstrate two technologies. One technology is what we refer to as electromagnetic formation flight, and that's the idea of using magnetic fields to control the relative positions and attitudes of spacecraft in a cluster. And the other technology is a form of wireless power transfer that would allow one spacecraft to transfer power to another spacecraft. And this hardware is being flown as an add-on to the already existing Spheres facility located on the ISS.
And the one of those that makes piques my interest the most is the power transfer. How do you transfer power between satellites like this without any cables?
Well, there are many mechanisms that one could consider for power transfer. This particular one is essentially an inductive power coupling. It's the same type of power coupling that you would find in a transformer. If you have an electric toothbrush, probably the charging station and the toothbrush operate on the same principle. Usually you have to have the primary and the secondary coils of the transformer in close proximity to get efficient coupling. But if the coils are actually tuned to the same resonant frequency, then you can get a much more efficient transfer of power between the primary and the secondary, even if they are separated by a fairly substantial distance.
That's really interesting. And so, what exactly are you trying to learn specifically with these experiments as they relate to your two major objectives?
Well, in truth, the real advantage of operating on the ISS is not so much for the wireless power transfer. We can demonstrate that on the ground. It's really focused on the electromagnetic formation flight because, while we can do experiments on the ground to demonstrate the principle behind EMFF, as we call it, we can only do it really effectively in kind of a two-dimensional setup where we could have multiple vehicles traveling, on a flat surface, on a what we call a flat floor, using air carriages. And we can demonstrate the principle, but the dynamics becomes much more complicated when you consider kind of the full 6 degrees of freedom, where we have 3 translational and 3 rotational degrees of freedom for each object. So by being able to operate in the microgravity environment of the ISS, we can really exercise the full control algorithm and dynamic capability of the system.
I noticed watching the experiment earlier this week that there were at times one of the rings experiments was anchored with bungee cords. What's that about?
So in kind of developing the technology, we're pursuing kind of a crawl, then walk, then run paradigm. And the first thing we wanted to do, this is our first science session, and in the first science session, to simplify the dynamics and also to make it easier for Mike to be able to conduct the experiments, we decided that anchoring one of the vehicles using the bungees and only have the other vehicle flying relative to it would be the easier way to go. In the second science session, we will most likely have both of the vehicles untethered. And so Mike's going to have to be able, or whoever, I guess next time, it might not be him, will have to be able to, initially position the vehicles and somewhat in the proximity of where we'd like them to be. And then because the control happens as a result of forces generated between the vehicles, both of them are going to be moving. The dynamics is much more complicated, as is the control.
Coincidentally, we're watching some recorded video right now that shows Hopkins positioning the two satellites without the bungee. So exactly what you were talking about, we're watching right now. Can you tell us a little bit about your background? Where are you from? Where'd you go to school? Where do you work now?
Sure. So I grew up in Western Pennsylvania, and I did my undergraduate degree at Penn State University. And then I moved to Boston, and I did my master's and PhD at MIT. And then I stayed there for 10 years after that. I was the associate director of the Space Systems Laboratory in the Department of Aeronautics and Astronautics for 10 years. And then in 2007, I moved down to the University of Maryland, where I established the Space Power and Propulsion Laboratory. But I still work very closely in collaboration with the folks back at MIT, and they actually were co-developers along with a company called Aurora Flight Sciences in developing this technology.
And do you have students involved in your research?
Sure do. So I had two students here, primarily two students here, graduate students. One completed his master's degree over the summer. One is working on her doctoral degree right now. And there have also been several students involved at MIT working on the control algorithm development as well.
There's obvious benefits to the work that you're doing for space vehicles in orbit or on long duration transfers to other locations in the solar system. Is there any application of your research that will help folks here on Earth?
Well, I think the primary way that it would impact, at least like the electromagnetic formation flight, it's really a space dedicated technology. Where it could help folks on the ground is in providing more capability for future space systems. And so using clusters of spacecraft instead of individual spacecraft will allow certain capabilities like getting higher resolution images maybe on the ground or in space, which could be used for improving weather prediction, things like that. The wireless power transfer has many terrestrial applications, and we're not necessarily leading the charge on that. There are several companies that are pursuing development of that technology to be able to power, let's say, small electronics like your laptop or your cell phone without having to plug them in.
Well, Ray Sedgwick, with Spheres Rings, we want to thank you very much for joining us here in Mission Control and explaining your experiment. We've enjoyed watching it on the downlinks today, and now we understand more about it. Thanks so much for being here.
Absolutely. Thank you.